Okay, so hello everyone. My name is Felipe Mazzi. I'm with the Brazilian team, and I'll be presenting to you today problem number 14, ice clock. So the problem statement tells us that if you place an ice cube inside a mix of vegetable oil and baby oil, it will remain between the two liquids due to its density. And we want to ask if this, and it will start to go up and down periodically in an intriguing way. We want to ask if you can turn this experiment into a clock, and what would be its longevity and precision. We want to optimize the setup to maximize those parameters. So beginning with the discussion of the mechanism behind the clock, we know that ice has a density which is intermediary to vegetable oil and mineral and baby oil, which is a kind of mineral oil made mostly of liquid paraffin. And the basic mechanism is quite simple. We know that the formation of high density water droplets will pull the ice downwards, as the formation of low density gas bubbles, as they escape from the ice, will pull the ice upwards. So we know that, I initially showed you this distribution of densities when you have a higher density on the bottom and a lower density on top. But of course, we need a smoother density profile in order to portray the phenomenon accurately. So when we do that, we know that the simple expression is just compensating the weight and buoyancy will look something like this. So we can write an expression for the time derivative of the vertical position. But in order to get an even more accurate the density profile, we were inspired by the literature to build a distribution like this one. So here's the reference which we use to obtain that. There's no analytical solution for the density profile at a planar liquid interface, but we will show that this is a reasonable approximation. And the general trend is that we fit the parameters A and B so as to have the density profile meet the known densities of the oils at the extremes. And so here I'm always plotting position, and pay attention to this, please. I'm always plotting position as a fraction of the height of the liquid column. So we fit A and B in order to adjust these extremes, and we fit beta to displace, we fit C to displace the equilibrium position between the two liquids, and beta will control the stiffness of the distribution. And usually we will adjust that as a best fit to our parameters. So now let's begin with a very simple, unrealistic, but bear with me, model. So we just have a comparison between the buoyancy and the weight forces. So, and we have an appropriate density distribution, which is shown on the graph on the left. And we know that the density of the ice is somewhat more tilted towards the vegetable oil. And what we do when we make the simulation is a result like this, which is a very nice, which is a clear oscillation, and we can do a finite Fourier transform just to confirm that there's a single frequency composing this result. So, okay, but this is still very unrealistic. We need to add more effects in our motion equation. So what we do is we add a damping term, which we do by assuming a low Reynolds number. The velocity of the ice is always in the range of a few centimeters per second. So we can use Stokes' law, which tells us that the drag force is linearly proportional to the velocity of the ice cube. So we can get a dimensionless factor to correct for the drag coefficient, which is found in the literature. And we know the viscosity of the soybean, which is also given in the literature. And what we get when we do the simulation adding this damping term is an oscillation. Well, obviously, it will oscillate a little bit and then it will stop. Next, we have to account for the presence of bubbles. What we do is to add square pulses corresponding to higher buoyancy due to the fact that air bubbles are much less denser than the liquids. And we can model this as shown here by the acceleration imprinted by the droplets on the ice cube as a function of time. And obviously the distribution of these in space will depend on the adhesion forces of the bubbles to the ice, the rate of formation, and the size of the bubbles. So here I'm always adding results to get to the final model. The fourth part is to account for the presence of water droplets. So here we may take into account, before we use the square pulses before because the formation of bubbles is virtually instantaneous, but to discuss the formation of water droplets, we may have to take into account the time dependence, which we remodel as an exponential phenomenon, which it must be the case, right? So it's similar to a charging capacitor, let's say. So once again, we can add, we do to the differences in density, but in this case, it will pull the ice downwards. Okay, so now what we get, so since the experiment requires a large amount of oil to perform, we initially start by looking at the video which is included in the problem description. So what we do here is we track the position of the center of the ice cube as a function of time. So this is the experimental data collected from this video. And here you can see the error bars, which are related to the tracking procedure. And now what we do is we take our model, we write down the times at which bubbles and droplets appear, looking at the video, and we input them into our theoretical model. So we take the data from the video, we put it in a model. So here it may seem like a complicated equation, but it's actually just a series of heaviside theta functions multiplying the acceleration due to the presence of bubbles and of droplets, the drag coefficient, and the buoyancy and weights. So and finally we adjust the density distribution to account for the best fit rate, right? So we have to correspond to the densities at the extremes, displace the equilibrium, and the steepness of the distribution is fitted. So when we do that, and we take these results and we compare the predictions of our model to the experiment, we get a very nice correspondence. So the orange continuous line is the prediction of the model based on the data acquired from the video, and in blue, the blue shaded region is the actual measured position. So we believe that this model seems to account for all the physical phenomena occurring here. But now we want to ask, more importantly, is it the clock? Well, we know that the model can replicate the experimental results with very good accuracy, but to measure time from the vertical displacement of the ice, we would need to know the density profile very well, and also the rate of formation of bubbles and droplets. And we know, for instance, that the density profile varies widely between types of oil, as you can see in this image. So we have corn oil, canola oil, and ricin oil. So this is a very important difficulty. And also, to get a smooth enough profile, you need a very large amount of oil, which is quite expensive. I should have converted the currency here, but it's quite expensive to do a large enough amount of oil to get a smooth density profile. So the third difficulty is obviously that bubbles are extremely hard to predict, and it depends on the procedure, the specific procedure chosen for ice formation. So we'd like to propose a different, arguably better clock, since we have discussed that the original idea would be a little bit unreliable, inconsistent, expensive, and hard to use. So what we do is we use the rate of droplet formation, right? So here's an ice cube put inside corn oil and baby oil, and we track the cumulative volume of molten water, which is deposited as a function of time for both vegetable oils. And what we do realize is that there is not just any radius which is allowed to exist inside this mixture. So we can calculate the maximum droplet radius by taking into account the surface tension between oil and water, and we can use a standard the standard test to make this measurement, and we can predict what should be the allowed radius of the droplets and compare it to the radius that's actually measured, and we see that we get a very good correspondence just by using these results. So there's not just, this is a key point, there's not just any radius allowed. The radius is specific to each vegetable oil. So if you know the radius, we can calculate the mass of the droplet. And if you know the mass of the droplet, we can calculate the amount of heat that is necessary to melt that amount of water. So here's the amount of heat that's actually absorbed by the droplet as a function of time. And we can make these plots. And if you know the amount of heat you need to melt the water, if you can measure the rate at which heat is transferred from the vegetable oil to the ice cube, and we model the vegetable oil as a thermal reservoir, which is our main approximation and the most important parameter in terms of optimizing our setup, we can actually get a measure of absorbed heat as a function of time just by using the thermal conductivity of the water layer and the temperature gradients and the area of an average ice cube made from a home freezer. So here's the model we're using, right? So we're assuming that the ice is surrounded by a layer of water. So we know the maximum heat which is allowed to accumulate, the rates, and we get a measurement that the time per droplets is about 89 seconds per droplet, with a precision of about 4 seconds every 1.5 minutes. Right? So if you buy an ice clock at your local store, all you have to do to use it is to add enough baby oil to keep the ice submerged, check the label to see how much heat is contained in each droplet, and you can also calculate from that the time. So all you have to do is count the number of droplets that are dropped from the ice, and then you know how much time has gone by. So this is the ice clock we propose. So in conclusion, we developed a model which accurately describes the vertical displacement of the ice cube in an ice clock setup, but we showed that the traditional ice clock, which you may expect to find by looking at the periodical vertical oscillations, is inconsistent, expensive, and hard to use, especially because density profile is very hard to model, and the behavior of bubbles is very unpredictable and depends on the method of ice formation. Lastly, we propose an alternative ice clock based on counting water droplets. It is mostly due to the fact that droplet size is limited due to the surface tension between water and vegetable oil. And we note that the longevity of the clock, as required by the problem statement, is limited, obviously, by the time it takes for the ice to completely melt. That the problem can be optimized by making it more similar to an actual thermal reservoir, which is also already a very good approximation, as we can see by the fact that our clock has about a 4.5% error every 1.5 minutes. So thank you very much, and I'm open for questions.
So, dear colleagues, my name is Ivan Polonik. I'm happy to be a part of the problem number 14 ice log. And so let's go to the main results of the report. Firstly, in the chronological order, we say that our ice goes down due to some water drops appears on it, on the down part of it, and it increases density, and that's why our ice goes down. So we agree with it. Next, that reason of rising is exactly bubbles going outside. So it's not point which we totally agree with, because let's see a situation. We have two oils with different densities, and we take it that density of oils, that density of ice is between these two densities. So after our drop releases from the ice, average density of the system is lower than density of the more dense oil, and our ice always goes up after drop releases. So I think that because of it, we'll have to describe the mechanism of rising more during discussion, but now we still don't, we're not sure about it's correct. So after it, we've gotten the equation for second-hand law with constant density, with some density distribution, but it's a question about applicability of the model, because in the model you have some smooth density distribution in the let's name bowl, in the bowl. But the question is if it's so an experiment, because it takes a lot of time to mix two oils, maybe up to days, because if you don't color one of them, you cannot be sure if you have this smooth gradient of density. And this is really that's things that you should describe more, and answer why is applicable. So next, what was done? You say that from the Fourier transform found that there's some frequency oscillation, so that's really good. In mathematical model, reporter added Stokes law of for resistance for spheres. So we agree with it, because the real system Reynolds number is small enough, about 5 or 10. So we agree with the reporter, but the problem is that Stokes law is written for spheres, but as you could see in experiment, reporter had cubes. So it's not exactly the same shape, and coefficient should change. And that's also not so strong points of the theory. But generally it could explain the phenomenon till they're going down, going to the bottom of the bowl. So next, about losing drops, it was not so clear for you. So you said that you took this surface tension depending on the temperature and took it for room temperature. But ice is cold. Its temperature is about maybe 5 degrees if it's warmed from the ice, from the oil. But it's much less than room temperature, is about 12 to 25. So your supertension coefficient will be different, and because of it, your results will be different. So now it's fine to with overview of report and go to some points. So about the theory, you explain the selection mechanism. I'm not exactly sure about it, but we will describe about it later. You somehow explained heat exchange, but unfortunately you didn't prove that you have stable temperature distribution in the system. You found parameters for drop before the separation and could predict ice dynamic, so that's really good. In your step, you excluded parallax effect, but there are also lots of things which could be improved, such as exact parameter of the drop during separation and how this separation changed by the dynamic. Also mixing of this size, and your presentation as a clock was poor enough. So if you can combine it all together, we see that you not fully understand what's the role of exactly two liquids, why not one. You investigated periodical motion, but not fully. You investigated real good role of three bubbles, but I think it's not the key phenomenon of the problem. And unfortunately, you missed most part of optimization and such things as precision probability of the clocks. So I think now we're going to the discussion.
Thank you very much for the points you raised. I'd like to begin just by clarifying, because many issues I think were maybe communication troubles, because for instance, when I talked about the surface tension, I thought you were asking what I considered the system, in which temperature I made the experiment in. It was room temperature. But the thing is that I measured the surface tension coefficient, right? So we did a test when you wait for there to be an equilibrium where the droplet is very nearly letting the ice go, which is a standard practice. And then I can actually measure empirically what the coefficients should be. And from there, it yields a prediction of what the radius should be. And what I did was compare the two. So there's no question that the surface tension was measured correctly.
Yeah, of course, yes. If you take it not from table but measure it, in this case, yes, it's okay. Yeah. So.
Okay. Well, another few other important points is that when it's Stokes' law, you were correct. It's made for spheres, but in our presentation we mentioned that we use a correction factor, which was about 0.92, and we mentioned also the reference from there. There is a standard way to correct Stokes' law for shapes other than spheres. So it was important of you to point that out, but that's something we did take into account. Just to...
I think let's stop sharing my presentation, go to your one, okay. And we'll talk about the physics of the process, divided it into parts.
Okay.
So I think let's have a discussion from what happens in canonical order when we try to make such experiments. So we take the oils, we put them inside the bowl, inside the bowl, and what happens there? So firstly, there's some heating between oils and ice. Do you agree?
There's some what between oil and ice?
Heating
starts. Heating, right? Okay.
So let's, I think, because of it, let's start from the heating, because it's not so because heating in the system is not so trivial. Firstly, because let's talk about the correction of your temperature. The temperature distribution is stable, because I mean, when you put ice with temperature about, let it name -5. Because it should be ice, inside the oil, which has temperature, room temperature, which is about 25. Temperature distribution is not stable for a long period of time because we have so big temperature gradient. It takes lots of time to become smooth. But in your model, you said that it's always smooth. Don't you think that that thing could improve your theory? And that's
sure. You're correct that the main point, the main contributor to uncertainty in our result is the approximation as a thermal reservoir, okay, which is equivalent to saying that the temperature of the oil doesn't change. About the heat exchange, we just model the ice as being at a fixed temperature and the oil as being at a fixed temperature, and they're separated by a layer of water whose thickness we measured experimentally. So from this model, we found an expression for the we found the thermal conductivity. Which is a table in tables, and then we can make a prediction for the rate of heat transfer, right? So that's the approximation, and it seemed to work, right? You're very right in pointing out that it would be better if we had, for instance, a larger recipient, so that it would be closer to a thermal reservoir. So you're right in pointing that out, but this is something that
and because of this
control, right?
I think it would be good improvement for you to estimate the time needed for this stable temperature distribution to appear. Not time of melting, but time for what your temperature distribution becomes stable. But okay, so let's.
Okay. It was just another point. Maybe I just want to be clear something. I just want to clarify something which was also mentioned during your presentation, which is that you mentioned about the fact that oils take some time to separate, right? Yeah. But this is important, but we did take that into account because we poured the oils very slowly so that there was there's little mixing as possible. And in general, you can see that they form depending on the type of oil, right? They can form separate phases, which are most.
I mean that if you have two different phases, doesn't it mean that your model from the fourth frame shouldn't work? Because on fourth frame you have smooth curve, but there I can clearly see this is not smooth density.
Yeah, no. For rice in oil, it's not that the model doesn't work; it's that the phenomenon doesn't happen, right? So in the picture on the right, the ice simply gets stuck between the two, because there's high viscosity contributing to it. But if the phase, that's one of the reasons why we abandoned the original ice clock, right? The original ice clock would require a very smooth profile of density in order for us to have real measurements. And that's expensive to do because you would need a very large amount of oil so that the transition would be smooth enough.
Yeah, okay.
So that's an important point.
As there is general discussion, if someone wants to ask a question, you may just write plus in chat and I'll ask you. So now let's continue our describing of the problem in chronological order. So what happens after the heat transition happens? Temperature of ice increase and it starts melting, yeah?
Yes.
As a result of it, some water appears and goes down as it has higher density than ice. Do you agree with it?
Mm-hmm. Yes.
Yeah. And at some moment, this drop separates from the ice. Yeah.
Yes. Correct.
Yeah. So let's try to find what is the parameters when this drop will separate, because it can't listen to infinity. Let's understand.
It will separate. It's precisely one of the main points of our clock is that the droplet will separate when it reaches a maximum rate.
But does the parameter of the drop depend on the shape, for example, of? So I mean, will the radius of the drop the same for the sphere and the cube? Or if it depends on geometry? What do you think?
You mean the shape of the ice cube?
Yes, yes. I mean shape of the ice. Can it influence?
It would probably not make a difference because it is excruciatingly slow. It takes a lot of time for the droplet to accumulate.
I'm sorry, but I have to disagree with it absolutely, because what we know about surface tensions, they are directed with some angle, contact angle to the normal of the surface. If you have sphere, normals of this shape, they are just lines connected with the center. But if you work with cube, normals are parallel. So, and because of it, even shape of your drops will be different with different shape of the cube. So go on. Did you check it experimentally, for example, how drop release from the cube and from the sphere?
No, you're entirely correct in pointing that in an ideal world that would be the case. A sphere would be different from a cube, but what actually happens in the experiment is that there is a layer of water which is formed around the whatever shape you have, and it grows and grows, and it slowly drifts to the bottom and then accumulates as a drop. So at the end of the day, it's always as if the drop, just a moment, it's always as if the drop is being held by a virtually straight layer of water. So if I could zoom in here, you would see that the shape at which the droplet comes into contact with the cube or the sphere is really always the same, because there's this layer of water forming between the droplet and the cube or the sphere, right?
So I still disagree with it, because saying such what, you miss dynamic of separation, because what happens in real life? We have some ice and water around it. What is has high density, and it goes down, and it's focused on down part of the ice. And since we have some dynamic of how this drop separates from it, and because of it, you can have it different for different shapes. But okay, I think let's agree with this. Disagree about this question, because we have some question from.
But just point out that even this is not remotely close to a straight cube, and the predictions hold very well, right? So this is a very messy surface, and still the predicted radius corresponds very well to the measured radius. So for both oils. So
question from
Oh yes, I have a question to the reporter. You investigate some droplets and bubbles that pull your ice into upwards or downwards, but did you investigate the period of some creation or some rising of bubbles and droplets?
We found that the rate of droplet formation, if I get your question correctly, is extremely hard to predict. It depends on how, for instance, if you boil the water before you freeze it, you get clearer ice. There will be less air in it. If you freeze the ice slowly, there will also be less bubbles in it. There are actually very known practices to reduce the amount of bubbles in it. But so that's why I didn't measure the rate. It's very hard to predict. And even then, to use the vertical oscillations as a way to track time, it would be virtually impractical.
I got your question. Thank you.
And we have a question from Maria.
Yeah, in your presentation, we saw you said we don't investigate the longevity and the precision of our clock, but in fact we did just for the clock we proposed.
Yeah, but I mean, but it isn't parametric investigation for these parameters. So you say it just in some case in conclusion, but the question of the problem was to investigate how these such parameters as longevity of the work of your clock, for example, depend on relevant parameters. Because if it's clock, we should measure time with it, and to measure time, we should know what time can a maximal measure. So the question problem was about it.
If you know the mass of your
guys, thank you for a nice discussion. We're running a bit out of time. So I would suggest to continue it afterwards. And now we can have a concluding remark from the reporter.
Okay, thank you. I was very pleased by the discussion. I think the opponent team raised some very important topics, especially concerning the discussion about the shape of the ice, which is not something we originally took into account. We were mostly concerned with the standard ice cubes one might have at home. But in general, I think our conclusions held up. There might have been some misunderstanding on what our aim was with proposing this different ice clock, because we wanted to make clear that our measurement of longevity would be due to would depend on let's say the size of the ice cube that you put into your system, right? That means that would determine how long the ice clock can work for. And we found that we made many approximations and we discussed them at length. And at the end, we got a precision of about, as I said, 4.5% every 1.5 minutes, which is satisfactory for a system as different as this one. So I think our conclusions held up, and I thank the opponent for the discussion.
Thank you. Now it's time for questions from the jury.
May I? I would like to ask the reporter, can you show me the slide where you compared your observation of the height with your theory? So you explained that you add forces corresponding to the water droplets falling and the bubbles rising. That's correct?
That's correct.
And the magnitude of these forces, are they calculated or are they fitted?
We approximate the bubbles as we measured the size of the bubbles once, and we say that all bubbles are virtually almost the same size. In general, it seems to work. And the size of the droplets, that's measured. It should have been in the table maybe, but so that's the magnitude is dependent on the volume, right, of the droplets. Okay. And that's why we. Okay. Right.
And to clarify, when you in the end listed the precision of your clock, how did you compute this precision? The 4.5%.
It's because there is 4.5% is just this comparison of 4 seconds every 1.5 minutes, which is here. The tau is the number of the uncertainty comes from our result for how much time does it take for a droplet to melt in this particular vegetable oil. And the uncertainties there come from, sorry, go on.
Is this the standard deviation?
No, this is a propagated uncertainty. So we get from for our measurements of what the maximum heat is and then the rates of heat exchange. These depends on our measurements for the thickness of the layer of water which is covering the ice and of the temperature gradients.
Okay. Well, thank you for answering my questions.
Okay.
Any more questions from other jury members?
Yeah. Have you tried to investigate how your precision evolves with time?
Yes, it's in general the precision will remain stable for as long as the ice cube is still melting. But naturally, if we approximate the system as a thermal reservoir, we know that the more the ice melts, the more the temperature will begin to change. So the precision will fade with time, right? But we do not quantify this amount.
Okay, and also like
small.
Question similar to what is present in a problem. So what's going to be your most precise clock? What should it be?
The most precise clock would be would have a very large reservoir recipient, sorry, a very large thing with a lot of oil in it, so that the temperature doesn't change a lot. And if we want more longevity, we need a larger ice cube.
But will size of ice cube also affect precision?
Mostly not. If the reservoir is large enough, no, virtually not.
Okay, thank you.
Okay, more questions? Jury members, don't be shy.
If there are no questions, I have a question to opponent team.
Sure, go
So, yeah, what do you think? Can a reporter combine two solutions and improve, like having a result from a second solution, from second clock they used, introduce this improvement in the first model, and would it improve model in general? What is your opinion?
So I think yes, that second part of the model, which was in the second half of the report, is a thing which should be took into account in the first one. And in this case, the reporter would be able to predict analytical motion, because so to describe the motion of the system, we should understand when the droplets separates from the ice and how ice hits. So knowing these two things, even with assumptions that reporter has, he would be able to predict.
Can I comment?
Yeah, sure.
So yeah, you're correct in saying that maybe we solved the problem of the rate of droplet formation, right? So that could be used to improve the first clock, but the problem with the bubbles would still be very significant. We could make bubble-less ice, but still you would have a problem in measuring the vertical displacement, because unless you have a very large recipient so that the density profile is smooth, it's very hard to get oscillations which you can measure consistently.
The next question to you: will bubble-less clock also work or not, in your opinion?
It will only go down and release the droplets and go up again, but it will do so. The problem is what we observe in the experiments is that this displacement is very small, especially if
yes, thank you.
Can I also answer?
Yeah.
Yeah. So as we could clearly see from the original video, we can. So after if we have a big bowl, as it was in the original video, after drop separates from the ice, it goes up always. It was just clearly seen in the video, and so it's not role of the bubbles. It just proves that you may see that it goes down after, just when drop leaves, it goes up, not because of the bubbles.
Yeah. So okay. Can I comment, or is there any other question?
Yeah. I mean, okay. 15 seconds.
As you can see in the graph, right? When it goes up, it's because there are bubbles accumulating and not yet being released. And once it accumulates a very large droplet, and once it releases, it goes down once and for all. So it's not. This would be a large enough system to perform the experiment with the original clock, but this is very hard to make in terms of expensive, being expensive.
Okay, thank you.